Right now, you are watching this video without a single physical wire connecting your screen to the internet. We rely on invisible connections every day, signals that reach through the air and hold our digital world together. But when we crack open a chemistry textbook, we get a very different picture. We see tiny spheres connected by rigid, solid lines. It looks like a microscopic construction set built out of wooden sticks. If you zoomed in on a real molecule, those sticks would vanish. In the physical world, there are no solid rods holding atoms in place. A chemical bond is actually an invisible attraction. It is a powerful pull keeping atoms locked in a dance, very much like the invisible Wi-Fi signal connecting your phone to a router. Once you move past the idea of rigid sticks, the subject changes. Organic chemistry becomes a story about atoms and the invisible forces that tie them together. Out of the 118 elements on the periodic table, only one gets an entire branch of science dedicated to it: carbon. Carbon has a specific superpower. It forms incredibly tight, highly stable, invisible connections with itself and with hydrogen. Carbon can lock hands with its neighbors and refuse to let go, building massive, stable chains that stay together under pressure. Here, a single carbon atom links with another and another, creating a continuous chain. Zooming out, these chains bend and fold into a vast molecular web. This is the structural backbone of everything from car fuel to the cells in your body. Carbon dominates chemistry because the invisible pull between its atoms is remarkably strong. Now, even though these connections are invisible, they aren't empty space. Those bonds are actually made of thick clouds of electrons. Because electrons carry a negative charge, these clouds act like matching magnets. If they get too close, they violently push away from one another. If a molecule were perfectly flat, like a drawing on a piece of paper, the electron clouds would be crammed together, constantly crashing into one another and creating structural chaos. To find stability, atoms fan out. They push away from each other and organize themselves in 3 dimensions, ensuring every cloud has enough breathing room. When carbon forms its 4 bonds, it balances them by taking on a specific 3-dimensional shape called a tetrahedron. To picture this, hold up 2 fingers like a peace sign. You get a vertical V shape pointing straight up and down. Looking at a second graphic, imagine your other hand making that same V shape, but turned completely sideways, so your fingers point forward and backward. Combining those pieces, carbon sits in the middle, arranging its bonds as 2 perpendicular intersecting V-shapes. When flattened out, textbook drawings strip away this depth, forcing everything onto a flat plane and making the molecule look like a simple cross. Recognizing this 2V structure reveals how molecules will actually interact, move, and bond when they meet in the real world. This illustration displays a complex chemical formula, exactly as it appears on a flat piece of paper. It looks like an intimidating maze of letters and black lines. This diagram illustrates looking past the flat lines. Visualizing atoms as 3-dimensional spheres reveals their true volume. As the model fades to transparent, the underlying geometry is revealed. Even complex structures are simply repeating patterns of perpendicular 2Vs. Navigating these complex chains simply means applying these same spatial rules over and over. Once you visualize these invisible connections in 3 dimensions, the flat drawings on a page turn into real physical objects that you can finally understand.